Thank you very much, Mr. Chairman. Uh, I'm going to talk about investigating the mechanism of conversion of a scabies treatment drug into an alcohol aversion drug, and we shall be considering its analog, their role in stabilization of all metal cluster aromatic compounds. So I come from Uday Pratap Autonomous College, and this college is situated on the north of the city. Uh, as you can see, towards the south is the BHU, and the north side it is the Uday Pratap College, very old college, established 1909, and has produced many luminaries, many stalwarts, among them the Prime Minister of India, late Prime Minister of India, Mr. Vishwanath Pratap Singh, then HRD Minister Arjun Singh, and the current Deputy Chairman of the Rajya Sabha, Shri Harvansh Narayan Singh. And it has produced many sports players, played for Indian teams and have performed very well, among them late Olympian Mohammad Shahid, Vivek Singh, present Indian basketball team captain Vishesh Prabhuvanshi, and Lalit Upadhyay, who is among the bronze medalists. He represented India in hockey in the recently held Tokyo Olympics. So let me start by acknowledging my PhD student, Mr. Vinit Kumar Singh, who has helped me in this project, and also to the organizers for providing me this opportunity. Well, there are a few persons who are very much addicted to alcohol, and when the problem becomes very tough for them, they have to visit a doctor, and the doctor prescribes them this particular medicine called dizone, which is nothing else but the disulfiram compound. And what happens is that once they take disulfiram, they start having intolerance for the alcohol, and the result is flushing, vomiting, and all kind of such effects. So because of that thing, they start abhorring alcohol. Now, there is another molecule called monosulfiram, and if a person has a scabies, say like rashes on the skin, and he visits the doctor, and then doctor advises him to apply this monosulfiram on the skin. So yes, he gets cured for the scabies, no doubt about that. But then he also kind of experienced the same stuff, the same effect that the person who had been asked by the doctor to take disulfiram, he also experienced the same thing. So that way, this particular drug, monosulfiram, has a side effect which is the same for alcohol aversion therapy, that means the disulfiram molecule. So this monosulfiram comes in the form of a soap, which is called monosulfiram medicated soap, Tetmosol. Many Bollywood actor and actress have been promoting this particular soap, and this side effect was reported by Lipsky in the year 1994. So what could be the reason that in presence of the light, this monosulfiram starts showing the similar properties as that of disulfiram? So first of all, let us try to see how alcohol is metabolized in the body. Well, there is one particular enzyme called alcohol dehydrogenase. It oxidizes it to acetaldehyde, and then we have aldehyde dehydrogenase, another enzyme which converts this acetaldehyde into the acetic acid, and subsequently it all gets converted to carbon dioxide and water. So disulfiram, what it does is it starts interacting with ALDH2, it inhibits it, and the result is that this acetaldehyde doesn't get converted to acetic acid, and so there's a huge accumulation of acetaldehyde which is toxic in nature. And a very small consumption of alcohol after disulfiram shows such very heavy side effects. Now, the molecule that we are investigating, monosulfiram, which is applied on the skin and used for the treatment of scabies, it shows a similar side effects as mentioned earlier. What could be the possible reason? What could be the possible mechanism also for understanding? Well, this is a monosulfiram molecule, and in presence of light, what we are seeing is that the disulfiram formation is taking place. So, we need to investigate the photochemical properties of this particular molecule, and maybe also of this particular one. So, it is assumed that monosulfiram, whether thermally or in the presence of light, gets cleaved. There is a homolytic dissociation taking place, so free radical formation is taking place, and one of the entity, this one, it recombines with another species of itself, and it leads to the formation of a disulfiram. So we developed the potential energy surface, potential energy profile for both monosulfiram and disulfiram. So as we can see, this one is the S0. So this one tells how a molecule behaves in a thermal manner, in a thermal mode, in the presence of the heat. So here we see the barrier for the formation of a free radical is close to 49 kcal per mole, which is something close to 2 electron volt. Now, if this molecule in the presence of light, it gets excited, so it's going to reach to S1, and S1 is this color, light blue color. So, and then we see its energy state, and we see the barrier, activation barrier. It is quite less in comparison to what we are observing in case of a thermal progressed energy state. So here we see it is 49 kcal per mole, and here it is something like 0.5 electron volt, which is close to 12 kilocalorie per mole. And where does this energy comes from? I mean, how much is the energy that a visible light has? Well, the spectrum ranges from 1.5 to 3 electron volts. So that means this particular molecule, monosulfiram, in presence of light, it intakes this particular energy from the visible light, reaches to S1, and the energy required for it to get broken into free radical form through homolytic dissociation is very less. It's 12 kcal per mole. So the first information we are getting is that it seems that this particular conversion, say from monosulfiram to disulfiram, which goes via the dissociation of the CS bond in case of the monosulfiram, is requiring very less energy in presence of the light. Now, as we mentioned earlier, that monosulfiram is this one, and it is getting cleaved at this carbon-sulfur bond, and that is why we have developed potential energy profile considering the CS bond. So one of the entities is this one, and it is going to recombine to form the disulfiram. So we need to generate a potential energy profile for disulfiram also, because this particular entity is this one only, and as we see that it's going downhill, and the energy required to cross this barrier is very less, and eventually it reaches to this point and it becomes disulfiram. So what do we know from this potential profile? Well, the cleavage of monosulfiram into free radical is possible both in thermal and photolytic condition. As we can see that in both cases we are going to have a free radical, this one also and this one also. Dissociation of monosulfiram in photolytic fashion is more feasible due to lesser activation barrier for S1 than the barrier observed for the S0PES for thermal dissociation. So we can see that this much is requiring this much energy, which is substantially large in comparison to this much. So it clearly tells that photolytic cleavage is very much possible in case of monosulfiram in comparison to the thermal one. Extending the study forward, we had this particular ligand, this monosulfiram and disulfiram, and we knew that if we break it in a heterolytic fashion, then we can have a dithiocarbonate anion ligand. Well, such ligands can get attached to metal in two manners. The first is one metal is combining with these two sulfur atoms, or the other two metals combining with this individual sulfur atom. So this one we are calling it as a 3-center, 1, 2, 3 center entity, and this one is a 4-center entity. Now, in literature, now we have metallic clusters which shows sigma aromaticity. We are all familiar with aromaticity in case of aromatic molecules like these, but when we talk about metal clusters, and that too M3 plus, Moldarev in the year 2001 showed that such kind of a molecule can show sigma aromatics. So sigma aromaticity is through sigma electrons, sigma bond electrons. So these are unstable due to positively charged, and these need to be stabilized. These metal clusters are positively charged. So our carbamate anion can stabilize such systems. So dithiocarbonate anion as a stabilizing ligand. We wanted to know how our anion would help in the stabilization of these sigma aromatic all metal clusters. So if we want to measure the aromaticity, we have two possibilities. The first is the NMR. So NMR tells you whether a particular molecule is aromatic or not. And the second way out is the nuclear independent chemical shift, which we can compute. So through computational chemistry, one can measure NICS mix value at a particular point, which is called the host atom, which is right in the middle of this particular 6-atom ring. And if we start going perpendicular to it, say like 0.5 and then around 1 Armstrong, so the value at this particular 1 Armstrong tells about whether this molecule can act in an aromatic manner or not. As we see here that till 1 Armstrong the aromaticity is increasing, mix value is negative, so negative means more aromatic, but as we go up it is decreasing. So next 1 is kind of a considered a benchmark for understanding whether a molecule can be aromatic or not. So these are some other examples in organic clusters where these clusters shows aromaticity. So copper 3 plus, Al4 2 minus. So coming back to our ligand and these all aromatic metal clusters, Cu3 plus. So we consider 3-centered bonding, we consider 4-centered bonding, and we had developed, we considered many conformations, many structures for this. So say for copper, silver and gold, this is a 3-centered bonding, and this one is a 4-centered bonding, which we are representing as a Pa2, Qa2 and Ra2. In order to know what kind of a bond formation is taking place between our sulfur atom and the metal one, so we computed the density, electron density, and the more this value, the more electrons are in between these two these two atoms at the bond critical point, and Laplacian value also tells about the same thing. So Laplacian, if it is a negative, then it shows that it has a covalent character, so here it tells that if it is negative, then we can and a high delta value, then it is a covalent reaction. So atoms and molecule, which was proposed by Bader, can tell us a lot about the interaction. So for a system containing 3D and heavier atom, it fails to explain the covalent bond. So in our case, what we are observing is that Laplacian is greater than 0, but then the HRC, total electron density, was lesser than 0. So we predict that this particular bond formation, it is a partly covalent bond formation taking place. We also developed electrostatic potential maps, and we can see that for these all metal clusters, this is showing blue, that means they are having these are electron deficient species. On the other hand, red one is the electron rich species. So when we allow both of them to interact, in a way, bond formation taking place. So what we find is that in case of this particular force-centered gold metal clusters, we see a green over here. The blue color is gone, so that means this center, which was electron deficient, is now more or less a little bit electron rich. That means electron from this ligand has got transferred to this one, which is also reflected at this particular point. Now we want to know how much these ligands help in the stabilization of or affects the aromaticity of these particular metal clusters. So surprisingly, we see that Ra1, which is this one, which is a 3-centered bond metal cluster, and this one is a ligand, this one is showing the maximum minus value. So minus value means more of the aromatic character. So what it means is that in such a case, the 2 electron which is within this particular metal clusters, they are not getting disturbed. They are not, or in a way, this ligand is not able to interact very much with the metal clusters. So as such, the aromaticity of the system is not disturbed. In fact, it is a little bit increased because of this particular ligand. But on the other hand, we see in case of the other metal cluster and the ligand interaction, the next value is decreasing. It is less minus 25 or something like that. So this tells that barring one condition, the ligand is not very much affecting the aromaticity of the system. In fact, they are decreasing the aromaticity of the system barring Ra1 system. So major finding of the study is that our analog anions, BTC anions, they are highly suitable for stabilizing electron deficient metal clusters. They are favorable with gold clusters as compared to the copper and silver clusters, and 4-centered complexes are more stable than the 3-centered complex.